Welcome back everyone. So today we are covering gradient descent technique. So in the previous presentations or the explanations, it was said that this particular technique will be covered, and here we are continuing on the playlist. So starting with this explanation, so just to understand the gradient descent technique in machine learning, let's start with the concept of convergence algorithm, because at the end of the day, we are using a convergence algorithm in this gradient descent technique to arrive at our uh, targeted or the desired solution. So what is a convergence algorithm? So this is how mathematically a convergence algorithm is denoted, wherein we find we move so we are trying to find a particular parameter, an optimum value of that particular parameter, and we start off with an initial value of that parameter, and we give it a direction and a magnitude to move on that graph. So this will be clear in the upcoming slides also, and in the um, explanation of each of these parameters. So for example, let theta be a parameter. So just to make it simpler, to make the explanation more simpler, let's say that the linear regression formula, this the line of this the simple formula for that linear regression line. If we say theta was a parameter, then theta naught and theta one. So let's say y is equal to theta naught plus theta 1 x, where theta 1 is the slope and theta naught is the intercept. So let theta be a parameter there, and let us take just theta 1 for the explanation sake as the slope. So now that parameter, we need to find the optimum value of that theta 1 value, of that theta 1. So just to bring in an explanation, this was this was a line wherein we can say that theta naught plus theta 1 theta 1 x. This is the equation of this line. So we need to find the optimum value of theta 1, so that this we can find the best fit line to the data, which can be used to predict the data which we do not have, for which we just have the independent variables, and we need to find the value of that dependent variable. That is what we covered in the regression explanations earlier. So if this theta 1 needs to be optimized, convergence algorithm is another way to find that optimum value. One way we learned was that differentiating and equating the function of theta 1 to 0, and then finding that minimum of that graph. So what happens is, this is how the RSS equation looked like in the previous explanation. This is the residual sum of squares. So, for example, this is theta 1. This was the parameter, the slope, and this was RSS. This is how the RSS moved. So it took the form of a quadratic equation, and it formed a convex curve. So what happens is, we need to find an optimum theta value. We use this convergence algorithm here, and we try to find out the optimum theta value, where we will get the best fit line, where we will get the best explanation. So this is how the convergence algorithm moves. The desired value of theta is reached by using an initial value of theta and subtracting the a value which is the step, which is also called the step. And this step is defined by using a learning rate which is fixed, and then the derivative of this the parameter, or the derivative of this RSS function, or a partial derivative of that function with respect to theta. So this RSS function could be for theta naught, could be for theta 1. If we differentiate with respect to theta 1, we will get the optimum value of theta 1 through this convergence algorithm. So parameter theta is, it could be weights in a machine learning model, or just as I said, coefficients in a linear regression model. Learning rate. So learning rate is alpha, which is a fixed parameter that we define, and we will see how this learning rate influences how this convergence algorithm works. The partial derivative of the cost function, or this is the part we are talking about here. So this represents the rate of change of cost function with respect to parameters. So the rate of change of RSS with respect to theta. So this is how this is the part of the partial derivative of the cost function. This is how we define this convergence algorithm, a through a basic explanation. So the derivative provides the direction of the steepest ascent or descent of the cost function at a specific point. So when we find a derivative of this RSS function at a certain point, the derivative will give the ascent or descent of this cost function. This is the cost function, and how this moves the gradient or the slope of this cost function at different points. The differentiation of this function will give us the slope at certain points, and we need to find this minimum value, and this algorithm will help us reach this minimum value, which will give us the slope which is zero, and the zero slope will give us the best fit line. So zero slope, what is happening when we find zero slope? We are finding the minimum value of RSS, which means we are minimizing that cost function RSS, and that is how we reach the optimum line. So let us go through some definitions of gradient descent. So these are taken from different sources. Gradient descent is a common optimization algorithm. So we were optimizing the value of that parameter, and we were trying to in order to find the best fit. So we were optimizing that parameter theta naught and theta 1 there. It is used to train machine learning models by training on data that these models can learn over time. So the USP or the key thing to note in this definition is the model is learning gradually over time, and we can define how gradual this process will be, and we can customize that, and that has its own advantages, which we will explain further in this presentation. Another definition: gradient descent is an optimization algorithm which is commonly used to train machine learning models and neural networks. It trains machine learning models by minimizing errors between predicted and actual results. So it is minimizing that cost function RSS. So one way of minimizing that RSS cost function was simply equating the derivative of that RSS to zero to find that minima value. And one way is to gradually descend through that graph of RSS. Instead of just equating it to zero, we will gradually descend. And why this gradual descension is required? Why not we are just simply equating it to zero? That will also be covered in this presentation towards the end of it. So keep watching. So gradient descent is this is another definition. It is used in machine learning to minimize the cost function by iteratively adjusting parameters in the direction of the negative gradient. So this is the gradient. So in this direction, it will gradually move to reach that minimum point. So this is what this definition is talking about. So it uses iterations. So we saw in that convergence algorithm explanation that it was moving iteratively, which means it uses an initial value, and then it moves from that initial value by finding different values through different values of that differentiation, or that the learning rate, and that step that we calculated in the previous slide. So that step will decide the iterations, the number of iterations, and how the iterations move towards that point of minima. So another definition, it is used to find the local minimum of a differentiable function. This is the key point here. Gradient descent in machine learning is simply used to find the values of functions parameters that minimize a cost function as far as possible. So this we will see in the upcoming slides. So how does gradient descent work? So now first we see intuitively through by way of graphs how this is happening, and then we see how this happens mathematically, and finally then the same is covered in the algorithm in uh, in Python and machine learning packages. So residual sum of squares, we are familiar with this concept. This is the cost function that we minimized to get that optimum value, and this is how it looks like. That was explained in the initial slide. So now, how does it work? Gradient descent. So suppose this graph goes something like this. So gradient descent will start from the steepest points. It will see that gradually we are reaching the gradient of this function is zero at the point of minima. So it will move in steps to reach there. It will take a big step from here to here, then a little step, then a little step, and this will be explained how it happens mathematically. How this step size reduces and how it moves from that steepest point to the least steepest or the zero gradient point. And and gradient descent only does a few calculations far from the optimal solution. The calculations are few here and they increase here. The step size decreases here and increases the number of calculations closer to the optimum value. So we see these are the number of steps that are happening in this algorithm. So the steps, these are few and far between. Again, this is decreasing, 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 and here the steps are maximum in order to find that zero value, in order to find that optimum value. So just to relate it with the linear regression line, this was our linear regression line. So for example, this is the data relating to height and weight, and as weight increases, generally what is seen as at higher weight is generally related to higher height. So this is the linear regression problem that we have here, and this is the cost function, the RSS, the sum of squares of these values, that RSS. So this moves somewhere like this, and this now is with respect to the intercept, not the slope of this line. Now we are trying to find the intercept. Now we are optimizing the intercept. So gradient descent will start off with an initial value, say here, and it will move on in large steps, and then it will move in smaller steps and finally reach here. And this point will give us the optimum value of this intercept. So moving on, so what is the mathematics behind this descent? So now this slide will cover only the mathematics part. Now we will try to relate it to the previous slide where we saw intuitively or graphically how the gradient descent algorithm moves in order to find that optimum value, to find that minima of that graph. So let's take a simple equation of a linear regression, y is equal to mx plus b. Now these parameters, these are the parameters where for whom we need to find the optimum values, and we initialize these parameters with some arbitrary values. It could be m, both could be zero, it could be one and zero, it could be zero or one or something like that, and we initialize this algorithm. So now we calculate the gradient of SSR with respect to each parameter. So as we said in the previous slide, we take partial derivatives of SSR with respect to M and B one by one, and the partial. So we will find the RSS function. We will differentiate it with respect to M and B, and through that value, we will use that convergence algorithm or the convergence formula to move towards the optimal solution. So this is what we get when we differentiate this SSR partial differentiation with respect to M, this is with respect to B, and this is what we get. So we already have values of M and B. We started off with certain values M and B, and now we find out the values of these two values, the partial derivatives. So in the convergence algorithm, if you remember that this was the partial derivative multiplied by a learning rate gives us a step size which is added or subtracted to the initialized value of M and B. We will take a specific example just now to understand it even better. So now these parameters are updated using a gradient and a learning rate. This is what I was saying just now. This gradient, now we know the gradient. Now we have a predetermined learning rate, which is denoted by alpha. So that was also covered in the initial slide. Okay, and this alpha is also decided when we run this model when we run a machine learning model, we have to optimize this value of alpha also. This is a part of the hyperparameter tuning where we need to find that alpha so that this method, the movement, is not too fast. We cannot move from here directly to here. We have to move gradually. So we have to have optimum value of alpha because alpha is giving us the step size. The step size consisted of alpha and this derivative. And once we have the derivative, we have the alpha. So we have the step size. This was the step size. And we move from this, the new value of M and B is found out using the step size and the previous value. And this new value and this is how this iteratively we find newer and newer values of M and B until we get the optimum values, until the the conditions are met wherein the number of iterations or the some parameters defining how much iterations will happen are met. So just using some initial values as an example. So let this be the equation mx plus b. These are the initial values. The let m be 0 and m be 1 and b be 0. Let alpha be 0.01. We get these values of derivatives. So we get the step size by multiplying these derivatives with the learning rate here. We get the step size. We subtracted the step size from the initialized value. This is a new value of m and b, and this will keep on happening iteratively until convergence happens. Convergence is the keyword here. So convergence is a predefined condition of either reaching the zero value of that slope where we will get the best parameter value or the number of steps until which these iterations need to happen. So just these three steps are now used here. Are we actually use some values into these, put some values into these three steps and get an outcome. So this is where the partial derivative with respect to m is being calculated, then with respect to b, and then we have the value of new slope and new coefficient here. And now after we getting these values, we used another iteration. These values become the old values then, and the new values calculated through the step size. For the step size, this is fixed alpha, and this is again found out using the latest values. So this, as we recall, this was the convergence algorithm, and now we see how the slope moves towards zero. So this has been taken from a stat quest, which is a must-watch video on YouTube. So this explanation is very simplified in nature. So we saw that we took partial derivatives with respect to intercept and slope. So this is the by d intercept represents the partial derivative with respect to intercept of RSS function, and taking three real time values or use case values, we find in this particular example the value of this partial derivative. And this partial derivative, as we recall, is used to determine the step size by multiplying this derivative by the learning rate or the alpha that we just saw. And we plug in this step size to get the new slope. And this is how it moves. So now we saw that until convergence happens in the previous slide. When does convergence happen? So gradient descent stops when the step size is very close to zero. This step size, this part is this part is constant alpha, and this will keep on decreasing one by one. So until it approaches almost zero, and as a result, step size reaches zero. This algorithm will keep on running until it reaches here. So please remember that this is a very simplified explanation. In real time, the number of parameters is high. It is not a simple two-dimensional plane or a simple linear regression of y is equal to mx plus c. In real time, there are higher number of parameters, and we have to imagine an n-dimensional space where this curve will look something like that. If you remember, the opening slide of this presentation had a 3D representation of such real-time curves that are there because so summarizing what we have learned in this explanation in this presentation, we first basically we are working on a convergence algorithm where a derivative of loss function, which was RSS in this case, was calculated. This derivative for each parameter. So if there are two parameters, say in a simple linear regression equation, which is the coefficient and the slope. So the derivative of this loss function is taking one first with respect to the slope, then with respect to the intercept. And in fancy machine learning language, we call that the gradient of the loss function. So the cost function and loss function are the same thing. It's just used differently in terms of when we denote it. So the cost function involves all the terms from initial value to the final value. Loss function is for that particular step or the particular point. So they're one of the same thing. The cost function is used to denote or to understand the entirety of that graph. So that's the same thing. So the gradient of that cost function or the gradient of the loss function are is found out. Then we initialize the parameters for both for the coefficient and the slope. We take some initial values. Now we plug the parameter values into the derivatives or the gradient as we saw in the machine learning lingo. So we are plugging in the initialized parameter values into the derivatives to find the derivative value. So from that derivative value and a learning rate, so this derivative or the slope into the learning rate, which is also predefined, we get the step size. And now the new parameter is calculated by subtracting the step size from the old parameter. So this formula denotes that we are moving towards the negative direction of that the slope or the descent. It is a negative descent that is happening. We are moving towards the zero slope of that function. Now, in real life, we come across large data sets. So gradient descent in a this was a very simplified explanation. In general practice, stochastic data gradient descent is used, where a subset of a large data set is used at every step rather than the full data set, because a large data set would involve a huge number of the time spent would be large to calculate the derivatives of loss function when the data set is very large. So we have seen how gradient descent works, but why is it used? Why is it sometimes more effective than the OLS method, the ordinary least squared method, wherein just we differentiated the RSS of the cost function and equated it to zero? So why is gradient descent used? In real life, the data sets are quite large, and gradient descent handles these data sets more effectively. As we just said in the last slide, a stochastic gradient descent method is used wherein it works on the subsets of the entire data. It cannot, if the data is in millions or even lakhs or even multiples of tens of thousands of rows or data points. So it is also effective in non-linear relationships, in capturing non-linear relationships where OLS might fail, because OLS will again rely on that cost function to be a simple quadratic curve, but it may not be the case. So gradient descent will work not just on that simple OLS kind of situation. It can work on a graph which has a number of minima, and it would be a higher dimension, n dimensions in nature. So gradient descent will work there. It is also effective in case of noisy data, wherein it will take care of outliers also, because it is moving gradually by through a defined learning rate. But OLS will be sensitive to outliers because it works on a simple formula. So here we are defining the parameters of movement towards that minimum value. So it is also more effective in regularization problems. It can be incorporated in L1 and L2 regularization. We also covered this in the previous explanations. If not, you can visit those explanations also in this on this channel. And again, a gradient descent can be parallelized efficiently, allowing it to take advantage of distributing computing networks, which can lead to significant speedup when dealing with large data sets again. So it parallelization means it can work simultaneously on a number of dimensions, and it can help us reach the effective the correct values or the most optimum values of parameters. Again, it can also deal with non-differentiable loss functions. So a function to be differentiable, it has to move in a certain manner. So this function is not differentiable. It has a the slope at this point cannot be defined. But gradient descent can also work in such functions. So this is why in real scenario, in real life, gradient descent finds more application than a simple OLS or the differentiating RS and equating it to zero, the OLS method. Gradient descent is more applicable, and more so today, these days, in deep learning algorithms also, gradient descent is another way to reaching towards that optimization of our the optimized or the optimum solution to get the best fit predictive the best fit graph, the best fit line, the best fit function, and the best prediction out of the existing data. Thank you, and do keep watching this channel for more and more simplified explanations of machine learning algorithms and concepts. Thank you.